from various ways which we are going to see, and you can use the information, whatever is information present about the receptor, which is your biological target. So we use that information for our de novo drug designing, and de novo literally means something which is starting from no is when you don't have any information about the ligand molecule. So you don't have information about ligand molecule, but you know about your protein target. So let's start building a ligand molecule which can bind to the protein target, and the methodology is called as de novo drug design. So we are going to use this methodology, and in consecutive slides we are going to see it, how it is being performed. So overall protocol which you can follow for the de novo drug designing, we also call it as a fragment based drug designing, because we start it from the fragments. Those fragments are the small molecules. Using those small molecules, we can generate a big molecule. So first thing is required, which is very minimum information which you require, is the protein receptor. The receptor, which is your biological target. You should know like what is your target against which you want to design a ligand molecule, or you should know the lock against which you want to design a key. Then next information which is required are the fragment molecules. So small fragments. So there are various ways to generate fragment molecules. So it is always better or suggested to generate those fragments from the known active molecules if you have that information available. If you don't have that information available, then yes, there are various fragment databases, or you can generate fragments from scratch also. So for that we have a script called fragment molecule.py. So we can just run this script on the given set of ligand molecules, which are the ligand molecules of your interest, or any type of ligand molecules. And this script will basically fragment all those molecules into small fragments, and then it will create a database of fragments based on your molecule. So if you are using those active molecules, if it is available, the information is available with you, then it's great. So you will have active fragment molecules at the end. So once you have fragment and once you have receptor, you need to perform initially the molecular docking of all those fragments inside the receptor. So for molecular docking, you can use glide extra precision or standard precision molecular docking, just to get better binding pose for all those small fragments, so that wherever those fragments get bind, it should bind precisely. So once you get all those fragments docked inside the protein structure, you will have the complete receptor fragment complex. So in which you have one receptor which has a binding pocket, and inside the binding pocket, or there are many sub pockets, all of those fragments which which are generated from initial exercise, all of those fragments get docked inside the protein. So once you have those fragments docked in particular pose inside the protein pocket or sub pockets, you collect those fragments, let's say some top fragments, top 10 or top 100 fragments, which are basically diverse in nature and present in different sub pockets inside the big binding pocket of the protein. So you take those top fragments, and then we have another tool called breed. So BREED. So with this breed tool, we can directly combine all those fragments in just one go. So you have dot poses of those fragments which are present in binding pocket or sub pocket, and then software will automatically combine all those fragments together by single bond, by adding some linker. And then once you have those molecules, you will have the molecule generated from the small fragments which are reasonable enough. So you can use those fragments for further molecular whatever molecules you get after combining all those fragments, you can redock all those molecules, or you can take it further for further virtual screening studies, or you can also perform a database search against those generated molecules. So this is what in general methodology which we follow for fragment based drug designing. And of course, once you get such molecule which is generated from fragment, we can check for the synthetic feasibility of that fragment, and we can check for the pharmacokinetic properties for that fragment. for those molecules. We can check also for the binding free energy for those molecules which are generated from fragment based drug design. And these all comes under the protocol of fragment based drug designing or virtual screening. So stepwise manner, if you see, we are going to see the example of P38 kinase. So its a crystal structure ID is 1W82, and you can see here in simplistic way I tried to explain how this works basically. So you have a ligand molecule which is present inside the protein structure. So this fragment molecule looks like this, and there are various single bonds which are present in it. So how this fragmentation works? So basically we can make various fragments out of this big molecule using this script called fragment molecule.py, and it tries to break the single bonds which are present in the big molecule and try to make the small fragments out of it. So one of the example of the single bond is this one, which is highlighted here, and there are many other bonds. So in this way, basically, this script will identify various fragments which are present in it. So currently, this particular molecule is divided into 3 small fragments. So one is in green color, one is in cyan color, and one is in magenta color. So once you have those fragments ready with you, you need to perform molecular docking of those fragments. You can see those fragments where these are present in the binding pocket. So basically it is occupying sub pocket of the complete big binding pocket. So according to their location, like you have various fragments done. So this is the way how it looks even before fragmentation and after fragmentation. So in this way, like whenever you have known drug molecule or known active molecule, that you can first of all take it for the fragment generation using the script. But in case if you don't have such molecule available with you, then of course there are many fragment databases which are available. For example, here is the fragment store, or here are the fragment libraries which are available for various fragments. You have even you have fragments for covalent binders. So there are many such fragment databases which are available from where you can directly use the fragment molecules for your fragment based virtual screening. So let's say you get this molecule either from database or from the fragmentation of your active molecules. So not necessarily you should have active molecules. You can take any molecule and make the fragment out of it, or you can take the fragment library and perform further fragment based drug design. So how it works, like once you have various fragments, you need to dock all those fragments inside the protein binding pocket. So here you can see this is the protein in surface, and there are many there is a big pocket and there are many sub pockets which are present here. So basically by using glide, you need to dock all those fragments inside the protein binding pocket. So according to the size of fragment and the properties of fragment, like wherever it finds perfect fit, it goes and fit inside the various sub pockets inside the big binding pocket. You can see here how all of those ligands which are fitted inside the pocket, means all of those small fragments which are fitted inside the big pocket and sub pocket, it looks like this. So you have protein and all pockets are being occupied according to their feasibility or according to the perfect fit of small fragments. So once you have this complete binding pocket occupied by the small fragments, this is what you need to do. Once you get those dock poses of fragments, what you need to do, you need to select some top 10 or top 100 small fragments which are present inside the binding pocket. So let's say this is the example. In this particular pocket, there are various fragments which are present inside the protein binding pocket. So one fragment is somewhere here, one is here, one is here, another one is here. These all fragments are docked inside the sub pocket based on their own uh, based on basically their own feasibility. So you don't need to worry about where it get fit. So there can be multiple fragments, there can be, let's say, 10-20 fragments which are occupying at the same place. So it does happen, so no need to worry about it. You just need to identify structurally diverse fragment set and which are present in various sub pockets. So once you get their dock pose, you need to take it and we need to basically join those fragments. So how to join it? So you can join it by single bond, you can join it by incorporating the ring in between, you can join it by incorporating linker in it. So basically this is what, when I say you can join it, so you don't need to join it, software do it for you in very quick manner. So you just need to identify reasonable fragments out of your fragment library which are docked, and once you have it, you can perform breed. Breed is the tool to combine all those fragments. So it basically joins all those fragments in the proper manner, and it also perform energy minimization on the fragment so that you get a reasonable structure out of it. So after joining all those fragments, you can see it has generated a complete molecule out of it. So which is also present inside the binding pocket in pretty reliable manner. And if you compare this, whatever the ligand molecule which is generated from fragment based drug designing with the previously known active molecule which is shown here in green sticks, so you can see it is almost superimposed on the top of each other, and it occupies the same binding pocket in, and it is also bound in the same fashion, like this phenyl ring is present at the same position, and there are hydrogen bond acceptors or donors which are present at the same position, and in this way it has occupied the same position inside the binding pocket. But the only advantage you have here is you have completely new molecule from nowhere. And now I mean, because it is completely new molecule, so you can also think of skipping the existing patents, and you will able to discover a new molecule which can be even patentable. So this is the way actually it works to combine all those fragments. So coming back to our first point, like you have got all fragments got docked inside the binding pocket of the protein, and it looks like something like this mess. So if you see all those ligands, all of those ligands are being docked, and these are present in sub pockets. Maybe in single sub pocket there can be 10-20 fragments which are present, but overall it looks like a complete mess. But this mess is going to give you the completely novel molecule out of it. So once you have this all molecule dock poses, the fragment poses inside the binding pocket, you just need to take those poses, and there is a module called breed. So you just need to provide those dock poses of various fragments as an input to this particular panel, and then panel this breed module will do the job for you. Like you just need to provide those fragment and click on run, so it will automatically generate all those molecules from your fragment molecule. So for example, you can see there are various fragments, and by using this breed you can basically generate a new molecule out of it, and there are various iterative process to generate the molecules by matching bond, by adding linker, or superimposing it with the existing structure. So in this way, basically it creates a new molecule for you as a breed exercise. So how it does, so as I explained, like it joins all those fragments by forming bond in between. We call it as a joining method. It also forms the link, means it can add additional fragment, small fragment inside while generating a molecule. So basically with this tool, it applies all those methodologies, and it tries to generate a new molecule for you using joining, linking, or the attachment. So for example, here is the one of the classic example, like with estrogen receptor, there is a inbound ligand which is present. So we have generated two different fragments from these molecules, and similarly for COX-1 protein, we have a bound ligand, and we have generated three different fragments out of it. So let's see how software joins all those fragments. So software can join those fragments by putting it in a binding pocket, and with the same positions you can join those fragments. And it also applies the linking methodology. So for example, you have a bunch of fragments here, you have a bunch of fragments here, and it gives a linker group like a phenyl ring to which acts as a linker region, and it will generate a completely new molecule out of it. So in this way, basically in background it works, the breed panel works. So another one of the very successful example here is mm, this particular study is present here in the Journal of Medicinal Chemistry. It was published in 2004. So in which they have performed this fragment based drug designing on HIV protease structure. So they had various structures from the different, the protein called HIV protease. They had different PDB IDs, and various like inhibitor was bound to the complexes. So you can see there are various ligand molecules, basically the known inhibitors, which are shown in different colors. And by using again the same methodology called fragment-based drug designing, they have combined these fragments in very different way. Like initially they generated fragments out of those molecules, and then they joined those fragment molecules. And you can see, you can observe here there are different colors of basically this ligand which are coming from different particular inhibitors. And after joining those, whenever they check the activity, they got tremendously higher activity, which is in nanomolar range. And you can see by combining all those fragments in very random way, they could able to generate the uh, very good active molecules out of it. So, and there are various generations of even combining. So when it combines those fragment and generate new molecule, and in this way it goes on. And you can see here in second generation of this combination, it has also generated a new molecule which is again more active in nature. So in this way, this fragment-based drug designing methodology works basically. So you have known molecules, make fragment of it, perform docking, and provide those docked fragments to the breed, and then breed will generate new molecules for you, and then you can use those molecules for further studies. So this is what was all about fragment-based drug designing, and now we will see some of the ligand enumeration tools which are present in the Schrodinger. So enumeration means you have a ligand molecule and you want to generate further more structures by performing various substitutions. So there is of course logic behind performing substitutions, but so the way is either you can draw those multiple structures by your own, or there must be a tool which can do all that job, which is automated, and you can just click on run and it will generate ligand library for you. So these are the various ligand enumeration tools which are present with us in the Schrodinger soup. So which are those names? So you can remember the names like R group enumeration tool is there. We are going to see it. We are going to see everything, and let's see, like in R group enumeration, basically you can perform various substitutions on it. Then there is something called pathfinder. So pathfinder here signifies a synthetic path of the molecule, how to synthesize that particular molecule. So software predicts that route for you, and by using that synthetic route we can perform reaction based enumeration. So there are two types of enumeration, like R group enumeration just for functional groups, and reaction based enumeration is for the based on the known reaction through which you can synthesize that molecule. So you should not miss the synthetic feasibility of any molecule, because until unless you synthesize that molecule, we cannot test it further using experimental techniques. So other methodologies can be bioisosteric modification. So this is also we are going to see, and the breed and combine fragment methodology we have seen, like how to combine those fragments. So first methodology, which is R group enumeration, you can see here you have a molecule, the structure of molecule, and what you need to do, you just need to open the panel, you need to select the atom where you want to perform modifications. For example, here I have picked two different atoms which are R1 and R2. So at this particular position, I wanted to make a substitution. So to make those substitution, we have this panel, and you can see there are various libraries. So basically those are various functional group libraries. We call it as R group library, which consists of various functional groups which are even specialized functional group. For example, there is a group called diverse R group. There is a group called solubilizing R group, which has functional group responsible for increasing solubility of the ligand. So in this way, logically, we can use this ligand library, these R group libraries, to perform substitution on it, and that's it. Just after performing this particular library generation, we can generate. You can see here there are 1,849 structures which are going to be generated just by performing substitution on two atoms using this R group enumeration tool. You just need to specify where you want to make substitution and click on run, and software will do the job for you, and it will create a huge library for you based on your requirement. So you can see this all those 2D structures which are present in the library. Their names are also given according to the substitutions which made on this R1 and R2 group. So you can see all those structures in 2D representation. But one of the very interesting thing is somebody may ask, like, those R group libraries are which are inbuilt, which are present in the software, but can I create my own R group library? Because R group library can be of my interest, so I could create whether I could create it or not. So the obvious answer is yes, of course, you can create your own R group library, which you think these are the substitutions are of my interest, or these are the substitution which I could synthesize in my chemistry lab. So yes, there is a tool for basically designing your own R group library, and you can provide smart pattern for it, or you can draw those small functional group and point of attachment, and in this way you can create basically your own R group library which you can use it for the further substitution. So this is the way, means every option is present. Only thing is you need to know what you wanted to do, and that's it. You can do it with Schrodinger. So the next tool is basically Pathfinder. So Pathfinder, as I already said, Pathfinder here is something which is for synthetic route prediction. So for that we have a tool called reaction based enumeration. So the panel looks like this, in which you have option called Pathfinder analysis. You just need to load your structure. You can draw your structure, or you can load your structure directly. Once you have structure, there is a button called generate pathway. So it will automatically identify all possible pathways through which you can synthesize this molecule. So here you can see there are list of pathways like alkylation or amination or second way of amination or Nagishi reaction or Suzuki reaction or using urea reaction. So there are various reaction pathways. It gives you as an output, and you can choose which pathway is reasonable for you, which can be possibly used in your chemistry laboratory or your collaborators laboratory. So for example, here once you have this reaction pathway, let's say I'm interested in alkylation pathway. So I have two reactants and the product is my compound, which is original compound. So means two reactants are there. So using these two reactants, I could basically generate a library of compound by substitution, by performing substitution on reactants, and it will lead to the basically different molecules with enumerated molecules from starting from my initial structure, and it will generate a library of compounds based on this particular reaction. So for this we have various reactants. You can see here there are reactants which you can mention here for reactant 1 and reactant 2, and there are many such again small substitution libraries which are present which favors this particular reaction. So we can directly use this information for the designing of designing of compound or enumeration of the original compound, which will lead to the different R1 and R2 group, which can be synthesized again through the reaction pathway of my interest. You can also apply some property filters on it, and there is a single button which is called enumerate. If you simply click on enumerate, it will create a huge library of compound that you can basically change this number if you are interested in 100,000 or 10,000 or more than that. So in just one go, it will create all that molecules for you. So you can use this various structures, and you can also use various these filters which are present with us. Filter means, for example, log P or property filter or solubility filter or number of atoms or molecular weight. So using this enumeration panel, you can generate all that structures in just one go, and all those structures are possibly synthesized through the reaction pathway of your interest, which you have chosen in first step. So in this way, basically we can explore this Pathfinder and reaction based enumeration tool. So basically there are advantages of it. So what are those? Like you can easily create this synthesizable um, library of molecules based on your reaction pathway, which is feasible in your laboratory. or you can also predict those all those pathways in retrosynthetic way. Then you can use this information for enumeration of molecules. So and at the end you can also generate chemically diverse type of compounds, but with the same synthetic feasibility. We can use it for basically, this tool is basically for the focused library generation. Focus means the generation of library not really random, but which is very much related to the your particular interest based on your synthetic scheme. So we can use this all information to generate a library. We call it as reaction based enumeration. Then next methodology comes into picture is bioisoster replacement. So this is also one of the famous methodology to generate a new molecule based on bioisosters. So bioisosters means nothing but the similar type of chemical group, functional groups, which are having different structure, but the properties are similar. For example, here it is acidic group we have, but acidic group has a property of hydrogen bond acceptor or maybe a donor. And the same thing with different structure, you can find it in a five member, this 4 nitrogen containing ring. So we can use it, such substitution, we call it as a bioisosters with the same property, same biological property, but different structure. We use this bioisostar replacement strategy in general to improve the potency or to enhance the selectivity of this particular molecule based on the bioisosters, or we can use it to improve the adiabatic profile, or if you want to prevent drug metabolism or toxicophores, we can use this methodology. And also we can generate novel molecules so that we can skip the existing patents for those molecules. So this is very well-known technology, well-known methodology, which is on which scientists are working on. So one of the example is, you can see here there is a precursor molecule, or its activity was 200 nanomolar, and pKa and log P is having moderate range. And this particular molecule is having this acidic functional group, but by using this bioisoster replacement, they have replaced it with another moiety which is having same characteristics but completely different structure. And you can see it also improves the log P value, but it retains the pKa, but log P is getting improved, as well as the biological activity is tremendously improved from 200 nanomolar to 19 nanomolar. So this is what the molecule is losartan. So this is what one of the use of this bioisoster replacement methodology. This is also included here. So how to do it? So basically this is also pretty straightforward panel. You just need to load your molecule, and there is a panel called bioisoster replacement. Just you need to provide your structures to this bioisoster replacement panel and click on run. So it will automatically identify with the fragments which are functional group which are present there in the structure, and which can be replaced by various bioisosters. So it automatically identifies and give you those molecules as an output. So this is also pretty straightforward panel which we have, because Maestro in Schrodinger you have all easy to use tools. So other thing which comes into picture is pharmacokinetic profiling of your molecules. So whatever molecule you have generated from your virtual screening exercise or through enumeration tool, it is necessary for those molecules to have good pharmacokinetic parameters. So for that there are many such pharmacokinetic parameters present with us. So you can use log solubility or blood-brain barrier permeation or CNS activity or log P, or there are various properties. Even you have some toxicities like hepatotoxicity or hERG channel blocking toxicity. So you can basically predict all those properties. You can also predict some descriptors like molecular weight or hydrogen bond donor acceptor count, or there are many such even polar surface area or polarizability. So these are various molecular descriptors which you can calculate, and the name of tool is quick prop. So using this quick prop tool, QIKPROP, quick prop tool, basically you can predict the activity of all those molecules in just one go. So it is tremendously faster. This is the name of tool, which is quick prop, and it gives you all those parameters. and it basically it is in background. Basically this tool is parameterized based on known drug molecules, and you can see how fast it is. It just process like 250,000 compounds in just 1 hour. So even you have huge library of compound, it will be predicted in as fast as manner. So it also includes Lipinski rule of 5 or rule of 3. So there are many such properties which you can get it which is resembles to the pharmacokinetic parameters. So you can use this as a filtering criteria. So in background, like each property is being calculated through the QSAR model, which is already built by the scientist and which is put inside the software. So you can see how this how reliable these models are and what is their correlation coefficient for each prediction of activity. For example, this is the graph for prediction of partition coefficient against octanol and water, and R square means correlation coefficient is 0.93, which is huge. So whatever prediction you get at the end using quick prop tool, it is very reliable, and the same thing is also applied to other parameters like Herb channel blocking or blood brain barrier permeability or CACO2 permeability, which is for intestinal permeability. So for all you have reliable models which are already put inside the quick prop module, and at the end you just need to click on run and you will get the reliable results out of it, which you can use it for the further screening. So also other than that, other than all those methodologies which you can apply for the ligand, you can also predict MMGBSA binding free energy using again a very fast, effective and reliable tool. So we have a tool called Prime MMGBSA, which you can find it in a Prime module. So MMGBSA is the method to compute binding free energy. So in this we have a simple panel called Prime MMGBSA, and in which you need to simply provide your molecular docking results. Whatever molecular docking results you get it from that molecular docking exercise, that file which is called as PostViewer file, which ends with the name pv.magz. So this is what is the output file of your molecular docking exercise. You just need to provide that complete output file to this particular panel, and it will, and you just need to click on run. It will automatically compute MMGPSA binding free energy for you, which is again more reliable than the docking score. And so this is part of virtual screening, like you perform initial molecular docking, you get docking score, you apply filter on it, and then you perform binding free energy calculations using MMGBSA, and then you apply second filter on it. So not only it runs on the static structure, but it also applies the implicit solvation model, and it can also apply some protein flexibility to the surrounding amino acid residue, means interacting amino acid residue, and it gives you the final reliable output as a binding free energy. So that binding free energy you can find it in a project table. So this is what you have. There are various tools which are available with you for performing virtual screening and for performing de novo, even de novo drug designing. So we are going to see each tool one by one, how it works. So, and most of all of those tools are pretty straightforward. Like you just need to load your molecule, open the panel and click on run. It will give you the output. Other than that, there are many other capabilities for drug designing. For example, shape-based screening, core hopping, or very recently came, which is Ligand Designer or interactive post prediction. So these options are also present with you. So shape-based screening means based on the shape of input ligand molecule, it tries to screen the data set and identify the similar shape molecule from the complete data set. And there is another tool called core hopping, through which you can identify basically the different scaffold, but with the the core of your molecule. Core means the biggest fragment of your molecule. If you want to change that particular core, so we can use core hopping methodology to identify different cores with the same properties. It is also just like a bioisoster replacement, but bioisoster is specifically for one functional group, but this is for the complete core of ligand, means the bigger structure. So this module is also available. Then there is a Ligand Designer. We are going to see it. It's very powerful and easy to use tool which perform all those operations in just one go. I hope you like it at the end. And there is interactive post prediction. Means you can perform molecular docking of the ligand molecules inside the protein, but in interactive way. Means you can design molecule and perform docking. You can design molecule and perform docking. In this way, interactively you can do it. So we will see it, all those tools in Maestro, how it looks like. So let me switch to the Maestro viewer. So first of all, like you always have, you know how to open the Maestro. You have Maestro icon on the desktop. You just need to double click on it and it will open the Maestro panel for you. So once you have Maestro panel open, so we will try to see one by one how this methodology works. So we start it from the first of all fragment based drug designing. So for fragment based drug designing, I have various fragments which are present with me. So I have a library of ligand molecules which I talked about. So these are various ligand molecules which are present with me. So let's say I have 50 ligand molecules. Either these are some known molecules or I got those molecules from the literature, or those are whether these are active or inactive, I don't know. But I have a library of molecules. So let's say these are the 50 ligand molecules which I have, and now I want to proceed further for the fragment based drug designing against the protein called 1FJS. So once I have this ligand library with me, so the very first thing you need to do is you need to make fragments out of these particular molecules. So I have placed this particular file, which is my 50 leads. This is the name of file which is with me, and I want to make fragments out of it. So to make fragments out of it, I have a simple script or simple command to run this fragmentation. So I can run this fragmentation in PowerShell. So there is an option called Schrodinger PowerShell. So you just need to remember this PowerShell option which is present in Windows. You can use this PowerShell to run commands, to execute few commands. And the same thing you can find it in Linux machine as a terminal. So you will have basically terminal as a as in Linux, which is same as that of your PowerShell. So initially I just once I open the PowerShell, I need to go to this particular directory, which is my working directory. So I have just copied the path of working directory, and it also has the same command as in Linux, like cd for change working directory. So I just paste the path, and now I am in the particular working directory which I have where I am working on. So I have a file called 50leaks.mae. So I want to make fragments out of it. So there is a simple command for it. You have just run fragment molecule dot py, and this is what the command is. You can try to see which are the options available with it using -h flag, and the command is same in Windows, Linux, or in Mac. So you can just simply run this command and see which are the options available for this particular command. So it is pretty straightforward command which has uses of just name of script, then input file, and the name of output file. So I'll just try to run this particular command again with the input file. So the name of input file is 50 leaks. The name should be correct enough, like whenever you pass the command, otherwise it will gives you the error. So after that, I just make the fragment out of it, right? So fragmented structures, let's say, and the extension is .mae, which is always supported by Schrodinger. So you just need to provide the extension. So you can see here the command is run fragment molecule, and run fragment molecule.py, the name of input file and the name of output file. So remember, input file should be present in the directory, and output file will be generated at the end of this command. So that's it. Once you have this command written, please write it correctly or note it down correctly. Just you need to click on enter and it will execute the command and it will try to make fragments of all of those 50 molecules in just one go. So you can see the output that it has generated various fragments out of those initial molecules and it is done. And you can see it has generated total number of output fragments which are 960 in number. So that's it. Once you have generated fragment, this one step is done. Now you have fragments with you and you can proceed further with the fragment based drug designing. So I have done the fragmentation of all those 50 molecules. So if I simply, if I want to load all those structures in the Maestro, so I'll just go to file, import structure and this particular fragmented molecules, right? So once you import those structures using this open button, you can see all those fragments which are in number of 960. So you will have all those fragments done for this particular molecule from this 50 ligand molecule. So you can go through all those fragments, or if you want to see all those fragments in just one go in 2D structure, you will have basically in project table there is a 2D viewer. So in project table you have this 2D viewer. If you simply click on it, you need to select first all those fragments and you can see this big molecule is get fragmented into small molecule. So in this way, basically, you can generate a lot of different structures out of it. So you can see there is a huge library of 960 fragments, which are small, big, and all possible fragments are already being generated out of all those molecules. So that can be small, that can be big, but fragments are there. So you need to use all those fragments for the further molecular docking exercise against the protein. So you have these fragments ready with you, you need to do docking out of it. So for doing docking, you must have the protein which is available with you, which I said like I'm going to dock all those fragments in the protein called 1FJS. So I have already prepared the protein structure using protein preparation wizard. So you can find this protein preparation wizard option here, and then you need to generate a grid out of it. So I have already generated a grid for this 1FJS protein and which is also present inside the directory. So let's see, you need to perform the molecular docking of your all those fragments. So for that you have an option which is called glide. In glide you will have option called ligand docking. So once you open the panel, you just need to provide the grid file which is already being generated with the name of glide grid. So in zip format. So we have this file called glide grid 1fjs.zip. This is grid file which I have already generated and placed in the folder. So you just need to provide this file. You need to provide this ligand molecules. Ligand molecules are nothing but your fragments. So we can provide it by simply providing this particular file which we have generated just now, fragmented structure.mae, and that's it. You just need to provide this file and it's done. Like in settings, you can choose the level of precision like standard precision or extra precision based on your requirement. It is always suggested to go for standard precision or extra precision, and that's it. Just click on run, and once you click on run, it will run the docking job in background. Like it will dock all those fragmented molecules, all those fragments in your 1FJS protein structure. So as an output of this docking job, you get all those docked poses for your molecules. So for example, here you can see this protein which is present in the surface view, and all those fragments are being docked inside the protein structure, and you can see here how these fragments are placed inside it. If I try to load all those fragments in just one go, so I'll just include all those fragments and let's try to see how it looks like. So you can load all those fragments in one by one, and you can see here all those green color ligand molecules which are present inside the binding pocket of the protein, and it occupies almost all of the space based on their size of ligand, size of binding pocket, subpocket, or properties of subpocket. So this is what the dock poses you have for those fragment molecule inside the protein called 1FJS. So as these dock poses are already sorted based on the docking score, so you can choose basically top 10 or top 100 dock poses which could cover the various structural diversity for this particular uh, for this particular protein structure and the fragment molecules. And you can see how these fragment molecules are placed inside the binding pocket, and though it looks like all are overlapping on the top of each other, but still those are small fragments, and we can use those dock poses of fragments for the joining means the breed exercise. So what we need to do, we just need to select all those molecules out of it. So I just load only those molecules. You can use the control button to load multiple molecules on the screen, or you can use shift button to load all molecules at once. So I have loaded all those molecules, and the molecules are also selected here in the table. So now our task is to combine all those fragments to generate new molecule. So for that we have a tool called breed. So breed means BREED. So you will find that option in enumeration section, or you can simply type it in a search bar and you will find this option called breed ligand creation. It is pretty straightforward panel. Like you just need to select your fragments, dock poses of fragment, provide it through file or through project table. So I have selected 19 entries from the project table, and that's it. You just need to click on run. So just provide your input molecule and click on run. It is pretty straightforward. All input parameters are given here, and it will automatically join the fragments to give you the new molecules. So that's it. Once you run this breed panel, you will see it gives the output of various new molecules based on your various fragments. So you can see here all of those molecules are joined based on their feasibility, and the fragments are given here. Sorry, the new molecules are given here. Basically, you can check those molecules in 2D. So let's see in 2D viewer, which is also present here in the Windows option, 2D viewer, and let's see how those fragments are being joined and new molecules are being generated based on those fragments. So this is the library of new molecules which you have from your fragment based joining. So once you have this library of ligand with you, so now our task is we can again dock the newly generated ligands using grid. So these are the new ligands which we are going to dock inside the again same protein structure. So there is a ligand docking panel again, like you have grid which is specified, and now you can basically provide your all of those entries which are generated from the grid exercise, and that's it. You can select it from the project table, or you can provide them from the file. So this is everything is possible, you know about it, and that's it. You just need to provide ligand inside the protein structure and click on run, and it will perform molecular docking of all of those fragments inside the binding pocket, and it gives you the output, molecular docking output of your all those newly generated ligand molecules from the various fragments. So you can see here how those fragments are being docked in, how those new molecules are being docked inside the protein structure. It also docked in the same fashion as that of our fragments. So because these molecules are generated from the fragments, then that's the reason it occupies the various sub pockets which are present inside the big binding pocket. And you can see this particular molecule has occupied only this sub pocket, but there are various other fragments which has occupied not only in that sub pocket but also in the bigger various bigger pockets also. You can see this molecule has occupied two sub pockets which is generated from this grid exercise, that big ligand. So once you have these ligands ready with you which are docked inside it, so you can see the docking score of those molecules which are present here. So you can find those molecules and their docking scores. So it has pretty good docking score of -10, 9, -8 in this way. So you can select this top few molecules for your further molecular modeling exercise, like because this can be a good binder out of it. So I will just select this top molecule which is having better score, which is minus 10.238. So I'll just pick this molecule for further modifications using probably enumeration tools which I could use. So this is the molecule which I have, and then I'll critically look into the receptor, like where this particular molecule is present and how we can improve the better binding by performing various substitution on it. So I could see like this particular molecule has occupied this particular sub pocket as well as this deep pocket, but there is also some pocket or some space available for molecule to get further expanded. So we can see here like if we perform substitution on this particular hydrogen, we can get a functional group which can bind here, or we can also make substitution to make molecular bind in this particular sub pocket. So just as an example, like I would like to perform substitution on this particular hydrogen of this particular ligand. So I know like there is a tool called R group enumeration which we have seen, and for that I just need to select this particular atom. So you can select this particular atom when your cursor is in A mode, means the atom selection mode. You can see it here. Now once you have this atomic selection mode, you can select the atom where you want to make substitution. So for that we have a enumeration tool which you can again find it in a task, and you can simply type enumeration and it will give you that R group enumeration option, custom R group. So you just need to click on this particular option. It will open the R group enumeration panel for you. It is pretty straightforward panel, and it also gives me the option like R1 substitution, because I have selected only one atom. So it has given me the particularly one R group, but if I select like two different atoms, so it will also give me the uh, two different R groups. Like for example, I have right now selected two atoms, so R1 and R2, and if I make a update from the selection, it displays the R1 and R2 groups. So there are two atoms where it is going to perform substitutions. So what you can substitute is, you can see there are various type of libraries of functional groups. So that can be your E molecules R group, which consists of 298 substitutions, means functional groups. Then there is diverse R group library which has 43 functional group. Then solubilizing R group which is responsible for increasing solubility of the molecule. Then there are ring decorations, and in this way there are many such functional group libraries which are present in it. But based on your requirement, you can think logically and you can proceed further with the further substitution. So right now, I just to save the time, I don't want to create a library, huge library of molecules. So you can see like if I choose two functional groups like R1 and R2 at two position, if I make a substitution of diverse R group of 43 functional groups, it will create a library of 1849 structures. Means at the end I will get 1849 number of structures in just one go. So you just need to select these groups, select your library and click on run. That's it. So right now, just to save our time, though it just take few seconds to generate that huge library, but currently I'll just go with only one position where I could make the substitution. So I just delete this particular row. So that's it. So I just want to make substitution on single point, which is given here. That's it. Yeah. And you can see first I need to remove all, then select one atom for substitution. Open the panel, click on update selection, choose the library of diverse R group and click on run. That's it. Once I click on run, within few seconds, it will generate a huge library based on this particular initial structure for me. And you can see it has generated a library of 43 molecules based on this particular functional group. And you can also see here like this particular functional group, it is added from the diverse R group library, and you can observe this how these various functional groups are present at this particular location. In this way you can check it, you can go through it, or if you want to analyze it in 2D viewer, so you have always 2D viewer option present with you, and you can see all those entries which are present here. So we have made substitutions at this particular carbonyl group. You can see here initial structure, then it has made a substitution of isopropyl, then tertiary butyl, then trifluoromethyl. So in this way it has made various substitution, even cyclohexane substitution on this location. In this way it has made all 43 structures in just one go. It just takes few seconds to generate that huge library for you. So now our task is to perform molecular docking of these enumerated structure inside the same protein to see whether it improves the binding or not. So again, to perform molecular docking, just go to ligand docking panel and provide your grid file, then provide your entries, this ligand molecules from project table or file, and click on run. Once you click on run, it will perform molecular docking of all those molecules inside the protein structure, and it gives you the output of all those dock structures. So you can see like how those structures are being docked. So I can simply load the protein in surface view just to see like how it looks like. So, and you can see here the aim of our exercise was we have created a functional group as this particular location to occupy this particular region which is present in the pocket, binding pocket. So that sub pocket is also being occupied by those ligand. So you can observe those changes, like the complete structure of molecule is same, it is still occupying those previously occupied sub pockets, but it also additionally occupied the new binding pocket of the protein. So based on that, you can see the docking score, whether it improves the docking score or not. So initially when we started our structure, we picked this particular structure from our initial docking, which has a docking score of minus 10.238. And then we enumerated this particular structure for further enumeration. And after enumeration, when we perform molecular docking of it, you can see the docking score got little bit improved to minus 10.504. And in this way, you will have other functional group which are being added. And because of that, the binding got improved based on docking score. So this is the way, like you first enumerate your molecule and then you perform molecular docking to see how it binds inside the protein structure. So once you have that thing which is available with you, so now we can see like whatever molecules you get it as a output of your complete molecular docking exercise. So let's say I have selected this particular molecule, but whether it is synthetically feasible or not, because we have generated this particular molecule not only from enumeration, but initially we have performed fragment based drug designing to generate this molecule. So it is necessary to check the synthetic feasibility of it. So for that we have a tool called reaction based enumeration. So you can simply type reaction based enumeration in the search bar and you get this option called reaction based enumeration. If you simply open that panel, it is pretty straightforward panel which you have. So it directly asks you to load the molecule either from project table or from workspace, and you have this option called pathfinder analysis. So I just load the structure. So this is what the structure of your ligand molecule which I have. So I initially, to perform synthetic feasibility, I need to perform this pathfinder analysis. That's it. So there is a button on the bottom right which is called generate pathway for this particular molecule. So let's click on it and you can see this particular molecule can be synthesized using Suzuki coupling reaction, and here is the particularly this reaction. There are two reactants through which you can generate this particular product of your interest. So this is the way basically you can see like whether you can synthesize this molecule in this particular way and whether if it is of particularly my interest or not. So this is what the reaction is. Now you can use this information, these two reactants, to generate a product. We can now use this information to enumerate this particular library using reaction based enumeration. So we just need to click on this define reactants. So define reactant is nothing but it gives you the proper format of reaction where you have R1 and AR is for aromatic. So you have reactant 1, reactant 2 and product. So based on this R1 substitution, and you can change this R1 or AR1 substitution, and it will still follow the same reaction mechanism and it will generate a same type of molecules. So for defining these reactants, you have reactant 1 and reactant 2. So if you see, there are various reactant libraries. So if you can see this library, so you can see here there are various type of reactants databases which are available. So for example, with just if you want to substitute alcohols, you can have this huge number of substitutions available. If you want to see like this aldehyde 2 halo groups, so you have 204, 204 functional groups which are available. So in this way, based on these reactants or reactant libraries of your interest, which are basically feasible for you to get synthesized in your laboratory, you can choose which type of substitutions I wanted to take it further. So for example, here I would take like acrylate amino type of reactants which are being substituted at reactant 1. So I just choose those one. So it will generate, it has around 852 number of substitutions. And for reactant 2, just to save time, like you can of course mention all those again those reactant libraries, but I will just maintain it at the original reactant. So only reactant 1 is going to be changed and reactant 2 will be constant. And according to reactant 1, which has acrylate amino substitution, it is going to generate the product. So you can see here there are various property filters also we have. For example, log P, molecular weight or chiral centers or number of hydrogen bond donor or acceptors. There are many such parameters which are available which you can use it as a filter. So once you if you are interested, you can use this filter, and you can also restrict the software to make number of poses like maximum number of products. Let's say it is by default it is 10,000, but just to save time, if I just want to generate 100 structures out of it, that's it. I just need to click on enumerate and it will automatically take these various reactants in reactant 1. It will generate this reaction and it will create these product structures just by clicking this enumerate, and it just take few seconds to enumerate this complete library. You just need to click on this enumerate option. So once you click on this enumerate option, so based on this particular molecule as an input, it will generate various basically fragment molecules for you, various molecules which are there. So you can see here. So I think I just close this panel. Yep. Okay. So you can see here it has generated this particular ligand molecule using our reaction based enumeration tool. And you can see there is another molecule which is also generated. So all those molecules are being generated based on the same structure which you have used initially and the reaction mechanism which you have chosen, which is Suzuki coupling reaction. And in this way you got new molecules which are generated using reaction based enumeration. So now our task is, because we have enumerated a library of molecule using reaction based enumeration. So our task is to perform molecular docking of those newly designed molecules using reaction based enumeration into the same protein to see how it binds. So I'll again go to molecular docking, provide grid file and provide the ligand entries, and that's it. Click on run. So once I click on run, it will run the molecular docking and it will give you the molecular docking results of all those molecules. And now you can see the docking score of newly designed molecule is also increased little bit. If you compare this docking score of your top ligand from which you have designed a new molecule, which has docking score of minus 10.504, and now it is increased to minus 10.691. So it means step by step it is being increased. So the thing is, this is the way basically you need to perform this reaction based enumeration or R group enumeration or complete ligand designing exercise to finally get the increase in docking score, means increase in binding. So let's say once you have these all molecules which are done, we can also basically we can apply some bioisoster type of replacement on these particular molecules. So let's see, this is the molecule which we have right now with us, and then I want to perform some bioisoster replacement on it. So as I said, with Schrodinger you have very easy to use tool, so you can just go to task and type bioisoster, and then it will give you this option called bioisoster replacement. So this is the option which you have. You just need to open this panel. So you have loaded the structure of your interest, and that's it. This is pretty straightforward panel. Just need to load your structure and click on run. Once you click on run, it automatically identifies the various regions where it can make the bioisoster replacement, and then at the end you get the output of your bioisoster replacement in just one go. So you can see, like from by using this structure, it has performed bioisoster replacement at this particular region of the molecule, which is shown here in the brown color or orange color. So, and we can also see here it has generated some other bioisoster at this particular location. In this way, basically, it has generated various type of ligand molecule which are new with new bioisosters in it. So wherever it is feasible to generate to place bioisosters functional groups, it does this exercise for you. So you can see, like this is the molecule of your interest, and now your task is to, again, whatever bioisosters you get it from the uh, software, like you have generated this library of newly designed molecule with new bioisosters. You need to perform molecular docking of all those molecules in the, again, using molecular docking, glide docking. And after performing again the same way, like you just need to choose this library, go to ligand docking panel, provide your grid file, provide your ligand molecules, and click on run. So once you click on run, it will give you the molecular docking output results, the same protein, and then you can see, like how it looks like. So after performing this bioisoster replacement, you can see it did not basically improve the docking score, but still the docking score remains more than 10, which is minus 10.352. So even after performing bioisoster replacement, you got the similar docking score, and we can use such molecules for further if it improves the docking score. So this is the way how bioisoster works. Then things come to the whatever docking poses you have. So whether can I stop at the molecular docking score for the analysis, or can I perform the binding free energy calculation? So to perform the binding free energy calculation, we have this particular docking results with me. So I just need to go to MMGBSA panel, which you can find it in task, browse, and in prime. So in prime, you will find the panel called MMGBSA. The same thing you can access through browse search option. So just if you open this panel, it looks like this prime MMGBSA, where it asks for the input file of Maestro pose viewer file. This pose viewer file is nothing but the output file which you get it from the molecular docking exercise. So just click on browse and see which file you want to give for the which you get it from the molecular docking. So let's say I want to use this molecular docking output file for the binding free energy calculation. So always remember, the molecular docking output file, which is pose viewer file, has name ending with pv.magz. So there should not be confusion with any other file name. Wherever you find the file name ending with pv.magz, it means this is the docking output file. You just need to provide this particular file to this panel, and that's it. Just click on run. It will run the binding free energy calculations in background for a few minutes, and it will give you the all binding free energy values as an output. So you can see this particular output. Once you get this output, it shows it in a column name called MMGBSA delta G bind. The same thing you can observe it from this particular property tree button. So you can see this is the property tree button which you have. So through which you can see there are various properties, and out of all those properties, if I'm not interested in all those properties, I'll just select all those properties and hide, right click and hide. And let's say if I want to see only the properties which are generated from prime exercise and the primary, and I am only interested in looking at the property called MMGBSA delta G bind. So I'll just select that particular property, and there is a tick option, and just on this tick option it will give me the binding free energy value for these all ligands, means the dot poses of all those ligands. At same time, if I want to see another property, let's say I want to see the docking score which is generated from glide exercise. So I'll just expand this glide option, then expand primary, and there is docking score option. I'll just click on this option called docking score. And now you can see the docking score of minus 10.352 has binding energy of minus 118.19. So in this way, you can have delta G, which is a binding free energy, change in binding free energy, MMGBSA. So it is more reliable parameter than docking score, which you can compute for your dock poses. So based on that, you can apply another filter for sorting all those molecules. So that's it. So now you got this binding free energy done for your molecule. So next thing you can predict is by after even binding free energy, you can predict the pharmacokinetic properties for your molecule. So for that, you just need to select your molecules, only the ligand molecules, let's say. So these are the various ligand molecules which you have selected in the table, and you need to go to task. There is a module called quick prop, QIKPROP. So quick prop, so please remember the spelling, it is QIKPROP, quick prop module. Yeah, so you can search it in a taskbar, and then it will give you the option called quick prop. Just open this panel. It is pretty straightforward panel. You just need to provide your input structure, which can be from project table, which can be from file. So once you have this 3D structure of molecule, that's it. You just need to give job name, any job name you can give, and that's it. Click on run. So once you click on run, it will run in background. In just few seconds, it will calculate all those parameters for you, which are your pharmacokinetic parameters, and you can see all those parameters are present in this table. And if you want to see those parameters again the same way like in property tree, you can see, look for the section called quick prop, means the properties which are generated from quick prop, and you can see which are all those properties which are mentioned here. So which also consist of all type of molecular descriptors, then pharmacokinetic property like solubility, CNS activity, and the hydrogen bond donor, etc., human oral absorption, and then log blood-brain barrier permeation, herb toxicity. So in this way, there are many such parameters which are present here. And if I want to see all those parameters, I'll just on this option, on this tick option, on these properties, and I'll see all those properties. And you can scroll this particular table through the table, and you can observe all those properties. So let's say, for example, I'm only interested right now in looking at log human oral absorption. So I'll just hide all those properties and only look for human oral absorption, and on this option, which is tick option in front of human oral absorption, and you can see it displays me the column of human oral absorption, which has some number written here, but I don't know what this number means. So for that, we always have help option with you. So just if I want to interpret these numbers, the numbers which are generated from quick prop, so just go to Schrodinger, you have help option, just go to help. In help, let's say I want to see the property called human oral absorption. Okay, so I just type, okay, this is what I wanted to see. So I just search for it, and it gives me, it is simple like Google search. It gives me the option for quick prop properties. If I click on it, it will give me the explanation of all those property and what those number means, what is the range of those number. So I'm particularly interested in human oral absorption. So let's say this human oral absorption, it says what does it mean by. So whenever it has value of 1, 2, 3 for low, medium and high. So 1 is low, 2 is medium and 3 is high oral absorption. So this is what how we can interpret this number. So all molecules which I have used are belonging to the 2 category. So means it has the medium oral absorption. So based on your criteria, you can choose different parameters for as a filter in your pharmacokinetic analysis, like quick prop properties. So this is what you can do with the Schrodinger, but maybe I would also show you how to perform shape-based screening. So it is also pretty straightforward. Like you have molecule, let's say you have a molecule present with you. So let's say this is the molecule of your interest, and you want to perform some shape-based screening on this particular molecule. Make sure this molecule should be correct with all hydrogen and everything. So this is the correct structure of molecule which you have, and you want to perform shape-based screening. So just go to task, and there is an option called shape-based screening. So once you type shape-based screening, you will find this particular option. Just go through this panel. It is also again straightforward panel. And the good thing is this particular panel is accelerated on CPU as well as on GPU also. If you have, it makes job faster. So that's it. You can use the shape query from workspace, and you can use the structures, means the database, the huge database like Zim database or PubChem database, whatever database you want to use. You can simply provide that particular file. So let's say I have already a particular database which is already created for me. So I'm just using this particular database for the screening. And let's say this is my database which I have generated. So let's see this database molecule which I have, and that's it. So there are various type of screening like volume screening or pharmacophore screening or atom type screening. So you can use these options. By default it works, and that's it. Just click on run. So you just need to provide your reference structure. You need to provide the database in which you want to search the query, and click on run. So once you click on run, it will automatically run the screening, and it gives you all those molecules which are matching with the shape of your input molecule as a output. So you can see all those molecules which you got it from the shape-based screening. So you can also use such shape-based screening for your virtual screening exercise. So that also you can use, and you can perform molecular docking of it. Then you can also use a core hopping technique. So core hopping also can be used for molecule, like for example, this is the molecule and for which I want to search for various cores. So there is an option called core hopping. So let's say core hopping, and I just type the core hopping, and it will give me the option called this particular core hopping, ligand based core hopping panel. It is also straightforward panel. You just need to define your template structure. For example, this is the arrow mark means, and there are two arrow marks basically. This one means from this molecule, from this atom particularly up to this atom. So you just need to do arrow mark means this is the defined template option. Like the template structure is between your arrow marks, and this arrow mark suggests the structure can grow beyond this arrow mark. Okay, so it can grow beyond this side, it can grow beyond this side. That's it. You can also specify some hydrogen bond donor or acceptors which are present on your template if you are interested in, but minimum thing is you just need to define your template, and that's it. There is option to specify cores. So those are automatically present inside the Schrodinger. So Schrodinger has databases of various cores which are present in your installation directory. You can choose any of the library. So let's say I choose the biggest library. So this number means the number of cores are present here. So I just choose this library, and that's it. So it will search for this particular core in this core libraries, and it will give you simply output of it. Once you click on run, it will automatically run it in a background, and it will give you the results of this particular core hopping as an output. So you can see as an output you will get these different cores which are specifically matched for this particular molecule. So you can see here it has matched the core, and you can, if you can find it out here, here is the, let me just change the color first. Yeah, so you can see here in green color, it was the initial input molecule in which you have provided this as a point of growing. So you can see this point is maintained and the other point was at this position, and it has looked for the similar type of cores, means the property is same but core is completely different at this particular location. So in gray color stick you can find the new molecule which has this type of core. So in this way basically you can get this different structures as a output based on this core hopping exercise. So this is where you can use such exercise for your structure screening protocols. So maybe one of the very interesting thing which I can show you is the particularly Ligand Designer. So you can find that option again in search bar called Ligand Designer. So you can see here there is an option called Ligand Designer which is available with new latest version of Schrodinger. So it is pretty exciting tool. So for that, I mean, we will see how it looks like. You just need to load the protein structure of your interest. So for example, I just load the protein structure called 21FJS. So it should be prepared. So it should be prepared through protein preparation wizard. So I just load this particular structure in the Maestro, and let's say how it looks like. Yeah, seems like the Maestro is frozen. So let me start the new Maestro. Yeah, okay. Yeah, so let's say you have a structure. Yeah, yeah. So let's say you have a structure, and I just delete those number of entries. So you have loaded this fully prepared structure for 1FJS, and you just need to start your Ligand Designer and see how it looks like. So once you start this Ligand Designer, the only button which you have is Analyze Workspace. So you should have protein ligand complex with you. Once you click on Analyze Workspace button, it will automatically identify the co-crystallized ligand present inside the structure, and you can see these blue clouds. So these are clouds, nothing but the regions which are present, which is the space, basically empty space present in the protein, which can be occupied by ligand. So you can see like how this empty space look like. So let's see it one by one. So you have ligand molecule, and here there is a space available. So with this space available, basically you can perform various substitutions at this point so that it can occupy the extra space of protein structure with you. So it is very much interactive in nature, like this is the structure of ligand which you have from the co-crystallized ligand. And now if I want to make some substitution, so I can basically see there is an option called this display ligand interaction, ligand receptor interaction. So if I on it, I can easily see there are amino acid residues. If you move simply mouse on it, it will show these interactions and the amino acid residues, and it will also show you like which interactions these residues are making. Like for example, this particular is making ring aromatic interaction, then this is particularly a hydrogen bond donor residue. So This is particularly acceptor residue. So interactively, it can show you all those options which are available around the ligand and which are present in the protein residues. So you can see there is nothing present at this position. So, and there is a void, means blue color cloud is for void. So it means we can use this void for further substitution. So there are various workflows which works very well. So for example, here I want to, let's say, attach R group. So I'll just say attach R group workflow, and I just need to select particular atom where I want to make substitution. So I just select here, and there is an option called enumerate, right? So I could see like which type of enumeration it is making. So as it is going on further for the enumeration, so let's say which is it uses default, or if you want to change the library, so I'll just go with the diverse R group substitutions, and that's it. Click on save, and there is a enumerate button. Once you click on enumerate, it will automatically start generating all those molecules, and you can see it is generating all those molecules here, and at same time it is also not only generating the library, but it is also performing docking of those molecules inside particular this protein structure called 1FJS, and you can see how this molecule looks like. It has generated substitution here or particularly here, and in this way you can see like how it interactively perform the docking also. And if you want to see the docking score, you can always see the docking score in project table, and you can see as it has enumerated all that library interactively, it also perform the docking of those molecules, and you can see the docking score. So based on that, you can select which is my best compound out of it, and then I can use it for the further ligand design. So this is what the powerful tool called Ligand Designer, and it also displays all those properties. It also has various options to see like ligand surface or receptor surface, or there are various workflows which are available, and all those things are very interactive in nature. So it is worth to give a try for this particular tool, which is very important, and I would say very interesting. So this is what all is related to the various tools which we can use it for the further virtual screening exercise. So here I would like to conclude the today's presentation and the demo session on various tools. So with this, I would again like to remind you, we always have help button with us, which answers all of your questions, and please give a try. With this, like I would like to acknowledge my team who are sitting in a Bangalore and working round the clock to answer your all of the queries and provide you all type of technical and scientific support. So thanks to all of you for joining us, and I can understand though it is too lengthy, but still if you have questions, so I would like to open the session for questions, and thank you very much again all of you for joining us and listen the presentation carefully. Thank you very much.
Thank you, Dr. Prajwal. We have received a couple of questions, so I'll just jump right into it. The first one is, could you please tell us the command to fragment the molecules?
Sure. I mean, it's pretty straightforward.
I think they missed it. Maybe it was not clear or too fast or something.
No problem. So let's see the command. So it's a simple command which you have, which is run fragment molecule dot py. Okay, and that's it. You need to provide input file dot .mae and output file dot .mae. This is the command that you have. Spelling should be correct. You might be surprised to know like you don't need this script to be present with you. It is already encoded in the run command, so you just need to type it correctly. That's it. It will give you the fragmentation for your molecules.
Thank you. So the next question is, so what is the, what difference is considered significant when there are close values of docking scores?
So you have seen so far like docking score values has a range of, let's say, -5 to -10 or -12, 13, something like that. So whatever docking score you get, if it is more the docking score, better, I mean more negatives the value, better the score is. But if you say like how significant it is, so first of all I would not consider docking score to maintain, to say the difference between two molecules. It is always better to go for binding free energy calculation to see the substantial difference in their binding energy. Docking score, again I would like to repeat the same thing, docking score is only there to just give you good enrichment. Okay, it is just to reduce your false positives. So always based on docking score, one should not discriminate between two structures. You always need to go for binding free energy calculations, then you get substantial difference.
Thank you. So the next question is, so when you receive, when you get these library of different compounds through, for example, our group enumeration, do we have to prepare these molecules, or can we directly take them for docking?
So you can directly take it from the docking, but if you want to go for ligand preparation, yes, you can go for ligand preparation, but it is not really necessary to go for ligand preparation because your structures are correct enough. So everything is being considered like it is 3D energy minimized and with proper functional groups. So you can take it further directly for molecular.
Thank you. So the next question is, if the Maestro crashes, does it start from the crashed point, or does it have autosave option, or do we have to set autosave options beforehand?
So, for to answer this question, these all things are already discussed in the Maestro demo. So you don't need to have this. You don't need to perform this autosave or anything else. Once you save your project, it is already saved. It has automatically auto-saved options. So you don't need to worry about it. Even your Maestro crashes, you can start it from the same position if you have saved this project initially. So I would recommend you to first visit the Maestro demo video, and then your doubts will be clarified.
Thank you. So the next question is, why do we have to use other tools if everything can be performed through Ligand Designer?
So Ligand Designer is the advanced tool which has basically this ligand design. The aim of Ligand Designer is to integrate all those tools into it. So before that, you have all those separate tools present in the Schrodinger, which is also now also it is present in a separate moiety. But Ligand Designer is something which is advanced and additional, where you have all modules integrated in one panel. So it just gives you the ease of usefulness.
Thank you. So the next question is, could we generate novel glycan ligands for lectin protein targets?
I think yes. So you can simply try the same methodologies to generate novel molecules. You can use fragment-based drug designing approach. You can use core hopping. You can use bioisosteric replacement. So just give a try. Definitely you can generate all type of novel molecules.
Thank you. So these are all the questions that I have received. As a reminder to all of you, if you still have questions, okay, one question just came. Um, would you recommend using kickprop before QSAR?
Yes, of course. My quick prop also gives you the properties and molecular descriptors. So those molecular descriptors you can use it for your QSAR model generation. Yes, and yes, of course you can use. So all of the tools you can use it at any given step of the virtual screening. It all depends on you. So it's you who is researcher who need to justify whatever you have done is correct or not. So yes, you can use it at any given point.
So that's all the question that we have received. If you have more questions, you can write to us at ddcourse@schrodinger.com. I'll just quickly share my screen for the regular announcements. Right, I hope you can see my screen. So as I already told you, there is a slight change in the schedule for this week's sessions. So if you want to see the upcoming sessions and how they have changed, you can just visit our website here, schrodinger.com/dd course. That is the course website, the course page on our website. So you can just quickly check the schedule if you're interested in checking what all is coming up. The other thing is about the office hours. So we are hosting office hours every Thursday from 4:30 p.m. to 5:30 p.m. on Zoom. The Zoom link is also available on the same page, schrodinger.com/dd course. So these office hours will continue even after this week. So since a lot of you have received the evaluation license and you're working on your own projects, you might have some questions. So obviously you can just join us during the office hours and ask your questions. You can also email us on ddcourse@schrodinger.com. That is also absolutely fine. But if you join us during office hours, you can also share your screens. We can take you around and check all the issues that you're facing. If you're facing any problems or if you want to ask something in particular, you can show your screen and we can help you solve the issues. The other thing is about the assessment test. You will be receiving a link at the end of this week. So in order to get the certificates, you have to qualify this test. Please make sure that you have gone through all the videos, all the video lectures, the theory as well as the demo sessions in order to qualify and study for this assessment test. So once you qualify this test, we'll be sending you an e-certificate. So the other thing is the SOC, the next session starting from November 2nd, the registration ends October 26th, which is next week. So make sure that you pay and register before October 26th in order to, take part in the next SOC course. The deadline is next week. So if you're interested to avail the discounted price, which is $125 as opposed to $350 and $475 for students and non-students, that's the regular price. With the discount code, you will get it for $125. If you do not have the discount code, you can write to us at ddcourse@schrodinger.com and we will send you the discount code. If you're facing any issue to register, you can also let us know. So we'll help you out in that. So in order to register, you have to go to this website, schrodinger.com/schrodinger-online-learning. If I think there are some questions, I'll just check them. So yes, if you'd like to purchase the Schrodinger software, you can write to me at shelvia@schrodinger.com. And I will, you can just maybe drop an email. If you don't have my email address already, you can drop an email on ddcourse@schrodinger.com and I will get back to you on the pricing. And if there's any other general query, you can also write to us at the same email. Other than that, I think I don't have any more announcements. So thank you for joining us today. I hope you thought it was an interesting demo session today. We'll have another session tomorrow. So please make sure that you join us at 10 a.m. in the morning for the live session. Have a great day. Thank you. Bye-bye.
Dr. Alex, we can close it.
Yes, sir. You can stop the live and you can close the Zoom.
Yeah, thank you so much.
Thank you.